Okay, the division algorithm theorem says if a and b are integers and b is positive, then there are unique integers q and r such that a is bq plus r with r is between 0 and b, including 0. So let's prove this one. Let's say the set T is a collection of a minus bk. A, b is already given, and k is any integer, but with the one condition that a minus bk should be non-negative. So let's say T is a collection of such numbers. One thing is clear, that this number a minus bk is a combination of three integers, so the result must be also an integer. And if you choose k is less than a over b, then this result is always greater than 0. And of course a minus bk is an integer, and it says that. So the t should include at least one of this style of integer. So t is not an empty set, and it's collection of only positive, right, or non-negative. So t should be a subset of the natural number set union the 0. We didn't cover this one in our course, but because of the well-ordering property, for any non-empty subset of natural number set has a least elements. So t satisfying that condition, of course with including 0, but still same thing. So t should have a least element r. Let's say it's r in there. Then clearly t is a collection of non-negative integers. Therefore r must be a non-negative integer. So r should be greater than or equal to 0. Then because r is an element of t, and t is a collection of this type of elements, so there must be some integer q exist and satisfying that r equals a minus bq. That's clear. So now let's prove the condition of r. We already proved r is non-negative. Then we need to show r is less than b for some q like that. So let's assume r is greater than equal to b. Then clearly r minus b is less than r, and r minus b can be written by a minus bq for r minus b. So after we arrange it, it looks like a minus b times q plus 1. But q plus 1 is also an integer, and this shape looks like exactly int, so it must be greater than or equal to 0. The reason is because we assume r is greater than or equal to b. So r minus b must be greater than or equal to 0. Okay, because we have that condition. Then what does that mean? Then r minus b can be written by a minus b times bq, which is in here, and that is an element in t, and that must be, because of that, is greater than or equal to 0, which is less than a minus bq. So when we started, our assumption was the r must be the least elements in t, but we found another integer which is in t, which is less than r. So that is not right. So it should be contradict with our assumption for r. Okay. Therefore, this assumption, which says r is greater than or equal to b, should be wrong, right? Therefore, r must be less than b. So now the remaining part is to show the uniqueness of the value q here. So let's assume there is another q just satisfying to get these results. which means bq1 plus r1 equals a which can be written by bq2 plus r2. Of course, r1, r2 must satisfy the part we already proved. So, with this condition or assumption, by the rearranging this, we can subtract this one from the left hand side. So, because we assume they are equal, so the result must be 0, and the arrangement giving us b times q1 minus q2 plus r1 minus r2. So it should be 0. Then r1 minus r2, or if you move this one to the left hand side, it changes to r2 minus r1 equals b times q1 minus q2, which means, by the definition, b is a divisor of r2 minus r1 because b is multiplied by an integer. But our assumption was r1, r2 is between 0 and b, right? And including, of course, 0. So r2 minus r1 must be 0 because r2 minus r1 is a multiple of b. Therefore, the only case for that should be 0, which means r1, r2 must be the same number. Then by that way, q1, q2 must be also same integer. Therefore, the q and r must be unique. And that's the end of the proof.